Our third speaker this morning is Professor Hyun Park from University of Minnesota. He's an assistant professor, and he's leading Shepherd Laboratory and working mainly on computer vision technologies. And today he'll talk about self-supervised behavioral imaging. So,
can you hear me?
Yes, thank you.
Right. Yeah, thank you for introduction and invite. And good morning, everyone. I'm Hyun Park from University of Minnesota, and I have been working on modeling 3D geometry of humans and animals using computer visions. And here I'd like to share the few samples of our research outcomes. Right, so this is my niece, Hannah Park, a daughter of my younger brother, who was born in 2016. And she was the firstborn baby in our family. She brought a full package of happiness to our family. Right? So, and a few months after she was born, she was diagnosed as oculomotor apraxia. So this is the absence of control, the voluntary eye movement, which means that she cannot control her eye movement. And so she has to turn her head to follow some objects. Right? So the main characteristic of this kind of disorder is they appear in the formal behaviors, gaze direction, facial expression, and body gesture. And this is the symptom that we can actually see from her behaviors. And more importantly, this leads to developmental delay. Okay, and actually, these types of the behavior disorder is not really limited to the oculomotor apraxia, but many different behavior disorders such as autism spectrum disorder, schizophrenia, and so on. Right? So in medical domain, there has been a significant breakthrough using AI and deep learning. For instance, IBM Watson that analyze MRI images and detect the diagnosis, even predict the future evolution of the disease, right? So, however, there's no such AI analysis for the behavior domain. So here I'd like to talk about the behavior image, okay, as opposed to the medical image. Okay? This is to measure, analyze, and forecast microscopic behavior signals using visual data, image, and videos. And in this talk, I'm going to just focus on how to measure our behaviors, how to model our behaviors. So yeah, back to this slide, oculomotor apraxia. This is known to be caused by the misalignment between our brain signals and our motor behavior, like our bodily movements. Okay, in her case, it was her eye movements. Okay? So there's a misalignment between the neural activities and the muscle movements. And actually, this has been widely studied in the neuroscience using monkeys because it is possible to implant microelectrode probe into the brain. So we can actually measure the brain signal directly from the monkeys. So here's like some seminal work by the Schwartz-Webb in the University of Pittsburgh. The monkey, yeah, now you see that this is a monkey that's strapped into some chair. So this is the arm of the monkey. And the head is rigidly connected to the neural recording system. Okay? And this has been a lot of neuroscientific progress with such a measurement system. Okay? And however, the system allows very restricted motion. For instance, the monkey should sit on this restricted chairs. Okay? So the question is, why do they require monkey to strap on the chair? Okay, there's two reasons. First, the electrode probe in her head need to be wired to the recording system, obviously. Okay, so we can record the brain signals. However, this problem is almost solved with the Wi-Fi transmissions. Okay, so we have some system that can address this. But still, so here I'm showing some example of monkey who wear this neural recording, portable neural recording rig. While she's freely navigating into the scene. So the monkey no longer sits on the restricted chair. Instead, she can freely move around the space with a full range of motion. But still, there is another reason that we cannot use these systems. As I said, the oculomotor apraxia is a misalignment between muscle movement and the brain signals. So we have to somehow correlate between the neural signals and body movements. So existing body measurement systems, such as a Vicon system that is used for the movie industry, uses this fiducian marker. You put the markers on the face of the actors, and then this camera observe these markers and then track this in three-dimensional space. Okay, this is how people have been using this marker for the movie industry or other medical systems. Okay? However, this is not applicable to the monkey because they are very sensitive and very uncomfortable with the markers. They always tear off these markers. So the marker is cannot be the solution. There's a fundamental limitation of using this marker-based systems. Further, to use the markers, as you see this is experiment, that we have to shave the hair of the marker, shave the hair of the arm because this hair can occlude the marker locations. Okay? So of course, this is a very invasive setup, negatively affects the natural behaviors of the monkey. Okay? So my goal here is to enable the markerless motion capture without markers for the monkey, as shown in the video in here, using just RGB cameras. Okay, so here I'm showing the one example where we predict the location of the markers of the monkeys without any fiducial markers attached to the body. Okay? So then one might argue that this problem is already solved in human domain because there has been remarkable progress in body tracking in human domain using deep learning. Okay? It is truly amazing that we can actually track these tiny fingers and the facial landmarks of this kid from this single cameras. Okay? However, this is not the case of the monkey. I will argue that the monkey tracking is fairly more difficult than the humans. Okay? So let's see how this deep learning or neural network works. Okay? So here's a neural network that takes the input image, and then it predicts the location of one of the landmark. For instance, here that we predict the location of the head, likelihood of the head. Okay? And the way it works is that there's an annotated data. So somebody label the location of the head on that image, which allow us to teach the neural network to mimic this behaviors. Okay? So the question is, where does this data come from? So for the human domain, there's millions of annotated data, which is labeled by the crowd workers. Okay? And people invest a lot of money so that they can actually label the landmark location, hand, legs, and then elbows for many, many different images. Okay? So this allowed them to train a neural network that can predict the human landmark properly. So let's see how much does it cost to generate such data. Let's do the simple math here. Okay, so I'm going to just do the math to calculate how much does it cost to label the large data set for human. Okay? So each annotation, it costs about 50 cents. Okay? And we need more annotation than instance because this is a crowd worker, so there are a lot of noise in the annotation. So we need more than annotations for the instances so that we can have a cross-check. Okay? And we need about 2 million of the instances to label. So it ends up with $10 million. Okay, so this is good, but I mean, still it's expensive, but it's still good because we can model entire population of human. Okay? What about the monkey? Okay, for the monkey, we cannot ask a crowd worker to label because the labeling is a far difficult task than the humans. Okay? It requires some prior knowledge. We need some biologists to label the data. Okay? So instead, I'm going to ask my grad student to label it, which is about like $30 per hour. Okay? And each annotation takes about 5 minutes. And yeah, there are trained labelers. So we don't need, we can reduce the number of annotation per instance. But we still need like the same amount of data, okay, to label. And that ends up with $12 million. So we need to spend, again, this $12 million for each monkey species here. Okay? Note that we use $10 million to model the entire population of humans. But here we can we model the monkey only for one species, but there's hundreds of species for the monkeys, right? So now you see that this is not scalable solution. So then how do we resolve this challenging problem? So my idea is a multiple camera system can significantly reduce the required amount of the annotation. That's my hypothesis. So let's consider this two images taken in the same time instance from different views. Okay? So this is one monkey that sees from different viewpoints. Okay? If we have a two image label, so I have a label of the shoulder, and then given this correspondence, so here I'm showing this camera geometry, two cameras seen from different viewpoint, and here's the location of the shoulder, let's say, and then we can triangulate it in three-dimensional space to identify the 3D location of this point. What is so interesting about this idea is that if we have, let's say I buy more cameras, I buy like hundreds of more cameras, then I can, by simply projecting this 3D reconstructed point to the other camera, I can have a free label. Okay? So just having more camera, I can augment my data. So to test this hypothesis, we built like a large camera system that is made of like 62 HD camera, which is called, we call this is the Open Monkey Studio. Okay? And that and these 62 cameras see some common monkey all together in synchronous. Okay, so this system creates the multi-view images of the monkey from the full 360 views, and with a high resolution, we can closely observe the monkey posture from the image. So great. So we can train the neural network with this augmented data. Okay. Again, we annotated two images, triangulate in three-dimensional space, and project to the many other view, okay, so that I can have augmented data. So I train a neural network that predict the location of the joint, and then this is like one of the results. So I apply this into unseen sequence, and yeah, it localized the joint location a bit, but the accuracy is not satisfactory at all. Okay? So the question is why this is not working? Why it failed to generalize to the unseen sequence? The main reason here is that the data augmentation allows to increase the data, okay, but only apply for the synchronized frames, okay, that are annotated. Okay? Because the 3D reconstruction is only available for that labeled data. Okay? But if you have, let's say, the 62 cameras and running over 30 frames per second, you get the more images, which you cannot even label. Okay? So you can only use this data augmentation scheme for the labeled data, but you cannot generalize for the unlabeled data at all. So this is significantly limit the amount of data can be used. So so the next question is, can we bypass the 3D reconstruction? The main limitation of data augmentation scheme that I talk about is we have to reconstruct the point in three-dimensional space. That's why the augmentation is still limited. But if we can bypass the 3D reconstruction, then maybe we can use the unlabeled data to supervise another unlabeled data. So I will talk about what do I mean by that. Okay. So consider this monkey image. Okay. So here is the location of the knee location of this monkey. Okay. And the pixel location of this X correspond to the ray in three-dimensional space. Okay, the pixel in a one image that corresponds to the ray in three-dimensional space. Okay? And if I see this ray from different view, okay, so here I'm seeing this monkey from different viewpoint, okay? And then that will be the line, the other image, and we call this is epipolar line. Okay? So again, the pixel in one image that translated to the line, corresponding line in the other image. Okay? What is so exciting, interesting about this idea is that if I know some information about one image, then I can transfer this knowledge to the other image. So again, and one interesting property of the epipolar line is that your corresponding point, so the knee joint of the second image, second view, that must lies in this epipolar line. And here's the linear equation that that describe this relationship. Okay, there's a fundamental matrix that maps the two view. Anyway, so the important message here is that what pixel in one image that correspond to ray in the other ray in three-dimensional space that projected image that give you the epipolar line, and my corresponding point in my second view that must lies in that point, that lines. So this is the beauty of the epipolar line, where we can transfer the information from one image to the other image. Okay? So now I'm going to talk about the deep learning. Okay? So I passed my image to the neural network, and this is my prediction. So this is the likelihood of the knee joint predicted from this view and these two views. Okay? Now, what I can do is I can apply the same idea. I can find the peak location from the maximum likelihood from this first image that give you, that is X star, and Y star is another, the peak location in the other image. And then, so this operation is nothing but argmax operation, right? And then we can plot this, this peak location to this epipolar constraint, and then we can form this multi-view loss for the neural network. Okay, we can use this neural network, the loss for the neural network. Okay. So up to now, everything looks mathematically elegant and beautiful. Okay. It's a very simple set of simple method. It should work. But however, there's a tiny problem that makes everything fails. That is, the deep learning requires all operation to be differentiable, because we want to backpropagate the error through this neural network. Okay, everything needs to be differentiable. Okay, but here, argmax operation is not differentiable. Argmax operation is nothing but you find the index that maximize some distribution. Okay, so finding this index is not differentiable operation. So to resolve this non-differentiability of argmax, we actually come up with a new idea that satisfies the epipolar constraint by passing argmax operations. So as I mentioned before, that the point in one image that corresponds to the line in the other image, and similarly, the distribution in one image that can be transformed to the other image that give you epipolar line distribution. Okay, so here's a distribution of knee joint, and this is the distribution of the epipolar line. Okay. So, and this can be actually computed by the epipolar pooling, very similar to the average pooling or max pooling used in the convolutional neural network. We actually defined a new differentiable operation that called epipolar pooling, which is finding the maximum location along the epipolar line. Okay. Anyway, okay, using this, and so why we can actually find the epipolar distribution by transforming the information in one image to the other image. Likewise, I have the prediction on this from the second view, and this point supposed to lies in this epipolar line. I mean, that's the definition of the epipolar constraint. Okay? So basically, by projecting onto itself, I get another epipolar line representation where we can. So now I have a two distribution. Okay? From first one is a transfer from the first view, and second one is projecting onto its own self So these two distribution must be matched. So we come up with this KL divergence, the measures that can measure the discrepancy of the two distribution, and by minimizing this KL divergence, we can actually train a neural network without any non-differentiable operation. Okay, full operation here is a differential. Okay. So in practice, we implement this idea as follows. Here's a neural network that predict the that takes the input image and then predict the location of knee joint here. Okay. And we have another neural network that actually is the same network that share the weight between this and predict the knee joint for the different view. Okay. And we go through this epipolar transformation that where we can measure the multi-view loss between these two images. And by enforcing this epipolar loss, we can ensure the geometric consistency between these two views. Okay. So optionally, when the label data available, we can add the label loss together. So one thing that I would like to note here is that if we ignore this label loss, so here from these two blocks here, okay, the multi-view pass, there's no requirement of having the labeled data. Therefore, the unlabeled data can supervise another labeled data. So one image can supervise another image by transferring information from one to the other, okay, which we don't need the label, ground truth label for that. Okay. So then that means I can use infinitely many unlabeled data for training on my neural network, which is going to be more generalized. Okay. So here I'm showing the effectiveness of the neural network training process here, where I'm showing the multiple view predictions. So here I have view 1 to view 8. We predict the left hand location. So this is the correct left hand location. But in view 3, I see that this because of the flip, you see there's some confusion, network make a mistake. And view 4, we have a very spurious prediction here and so on. Okay? And this is the before training. Okay? Before training. After training, as training process going on, you see that this error is corrected, automatically corrected, because neural network, this is the only location that is consistent across the view. Okay. And same for the left elbow here. So we predict the left elbow. Okay, so this is a correct location, but this network make a mistake on for the view 2, view 3, and so on. But by applying this epipolar loss, we can actually everything converge to the right solution because this is the only location that is consistent across a view. Yeah, so we use this idea to do the full markerless motion capture for the monkey. So here we record the free movement of the monkey that moving around the space freely, and then using this the detections to reconstruct the geometry, the full geometry of the monkey movement in 3-dimensional space. So this will give you the full markerless motion capture for the monkey. And the system that we have built is agnostic to the number of monkeys. Here I'm showing the video of the social interaction between monkeys. 2 monkeys are situated in the same environment where we can track their activities simultaneously that facilitated some kind of study, a lot of interesting behavior questions such as communications, reciprocal behavioral mirroring, ranking, roles, and sexual behavior. Right, so given such tracking system, now we are about to answer the core scientific question of how motor activities, how our muscle movements are modulated by the neural activity in our brain. Okay. So for instance, with this camera system, we can reconstruct the 3D body movement in the cage. Okay? And we can also implant the wireless electroprobe into the brain to measure the brain activity that are responsible for the motor behaviors and spatial reasoning, such as that corresponds to the brain regions such as motor cortex, frontal cortex, and the visual cortex, and so on. Okay? On the bottom right, I'm showing the spectrogram of the brain activity that will be correlated with our muscle movements. So our hypothesis is that there exists a strong correlation between our brain activities and the motion. So to prove this hypothesis, we designed a very simple neural network that can predict the 3D XYZ location of monkey given the brain signals represented by this spectrogram. Okay? This is model trained by the training data obtained from the OpenMonkey studios, okay? And then we apply this into the different data in different days. If the neural network is highly predictive of the 3D location of monkey, then this indicates that for the first time, we can study the relationship between the brain and the muscle movement. Okay. So here's like a preliminary result. Actually, I got this result a few days ago. I plot the XYZ coordinate. So you see that this is X-axis represents the time. This is XYZ coordinate over time. Okay. And that is measured by this camera system. So this is actually the motor activities. Okay. And then we have here I'm showing the prediction of the 3D location predicted by the brain signals. Okay. Of course, it is noisy, but you can easily see the patterns. So you can see that the long neural network is able to predict the 3D location using these brain signals, which means that by measuring the brain signals, we can predict where the monkey is located. And this indicates that there exists some reason in our brain that encodes the spatial location. Basically, if you go somewhere, there is some brain reason that tells us, yeah, the GPS locations without even that. So now we are extending this preliminary result in on the entire post, and this is a still ongoing project. So another research effort that we are undertaking is generalization. So this is the data set or the prediction model that we generate from this OpenMonkey Studio generalized. For instance, can we apply the model that we learned from the OpenMonkey Studio to the video that I took from the Minnesota Zoo? Okay. So here there are multiple monkeys performing diverse natural activities. Unlike the lab control environments, they exhibit very truly natural social interactions, right? Without any human intervention. Okay? So studying the behaviors in this zoo environment or the natural habitat is more scientifically impactful. But the model that we have learned from the OpenMonkey Studio, this is far from the generalizable because of different environment, the viewpoint, appearance, and even different species. Okay? So how do we address this? So let me just quantify the generalizability to see how much we are behind. So consider this a detection curve we're showing in the picture on the right that x-axis the error tolerance, okay? And y-axis is the detection rate. Okay? So each data point in this graph represents how accurate detection is given this detection tolerance. So if the detection tolerance becomes really, really tight, that means it's going to be my detection can be will be very, very rate will be very, very low. Okay? So if I have an ideal detector, perfect detector, so 100% accuracy, then it will give you the 100% accuracy with extremely small, tight error tolerance. Therefore, in this detection graph look like this is step function. Okay? So let's consider a very simple baseline here. I have a model that is trained on the human pulse data, such as the COCO data, where there's hundreds of thousands of annotated data for that. Okay? And this model is well trained because there's a lot of data. Okay? And the blue curve that I'm showing here is a prediction on the testing data that is on the human subjects. Okay? Training on the human and testing on the human. Okay? Now you see that the performance is not perfect, but it's close to the ideal detection. It's pretty good. Okay? Now I consider the same trained model and then testing on the monkey data without any domain adaptations. You see the significant performance degradation because the model is not designed for the prediction model, to predict the model, to predict the monkey. Okay? So we train the model on the human and then apply it to the monkey. Yeah, it works. It doesn't work. I mean, that's expected. Right? So now I'm going to change my model. Okay? Now I'm going to use the model that is trained on the monkey studio data set. So this is a monkey data. Okay? And then we apply onto in the wild the monkey image like a zoo data. Okay? So that end up with this orange curve here. Okay? You see there's some improvement from the human to the monkey prediction. However, the performance improvement is a very marginal and subtle. Okay? It's far from the human detection and showing group. So there's a significant gap between this blue and the orange curve that represent the domain difference. Okay? The model should be trained on this means that our model should train on the right data set to perform well on the testing data. And that means that the lab data that we have collected from the OpenMonkey Studio is barely useful for this task. So our question now is maybe if we have a new data set that can capture the testing distribution, we should be able to predict better. Based on this hypothesis, we actually collect a new data set called OpenMonkey Challenge data. It is composed of more than 100,000 of images with 17 landmark annotations, and these are from the internet, national primate centers, and zoos, and so on. So we collect the data, natural data, and also not only include the one species, we include the 26 different monkey species and ape species for this. So given this annotated data, now we actually launch a new post-tracking challenge to solve this challenging problem using this community effort. So again, the good news here is that the data set improved the performance significantly. Okay? So red curve that I'm showing here is the curve of the model trained on this OpenMonkey challenge data and test on the challenge data. And with the full amount of data I'm showing here, the dark red curve, the prediction is is approaching to the human level detection. Okay? But in the same time, it also illustrates the performance bound. Okay? There still exists a large gap between the human and monkey detections. The main source of the difference arises from the amount of labeled data. Okay? Number of labeled data for human is nearly order of 1 million. Okay? While the data of monkey is order of 100K. Okay? So the human data set is nearly 10 times bigger than the monkey data. So from this study, we conjecture that this gap can be filled by leveraging the semi-supervised learning. And so to study this problem, so we actually launched the OpenMonkey Challenge to attract more attention to attract the machine learning researchers to participate. So if you're interested in the machine learning problems, and please check out our website, openmonkeychallenge.com, and that provides annotated data, challenges, all the description of this challenge. All right, so I think I'm going to switch my gear to the different topics. So if you have any question, I can answer a few of them.
Can I ask some questions using the
Go ahead.
microphone?
Go ahead.
So, 한국말로 해도 돼요?
예, 예.
아, 이 지금 그 아주 헌보영인데요. 예,
예, 예.
오랜만이네요. 예.
예.
그 뭐냐 좀 제가 좀 이해하려고 하는데 아까 그 펀더멘털 매트릭스 써가지고 그 러닝하는 거 있잖아요.
예.
그게 정확히 뭘 러닝하는 거예요? 이게 사실은 오브젝트가 있으면은 그 펀더멘털 매트릭스가 다 다를 거 아니에요.
네.
그러니까 그러니까 오브젝트 포즈하고 로케이션이 다 달라도 그 매핑을 다 해줄 수 있도록 학습하는 거예요?
아니요, 그런 건 아니고 그렇게 복잡한 시스템은 아니고요.
예.
카메라가 칼리브레이티드 카메라가 있다는 가정하에
예.
그리고 오브젝트들은 여기서 러닝한 거는 키포인트 디텍터만 러닝한 겁니다.
아.
그리고 뭐 트랜스포메이션 이런 것들은 다 이미 칼리브레이션 된 겁니다.
그런데 그러면 이제 펀더멘털 매트릭스 계산할 수 있으니까.
예, 그거는 이미 기본입니다.
알겠습니다. 그리고 그 아까 그래프 있는 슬라이드 있잖아요. 네, 여기서 요 세 번째 오렌지색 말고는 그냥 2D 이미지 한 장에서 2D 이미지로 이렇게 트랜슬레이트 한 건가요?
예, 다 그런 겁니다. 모든 게 다 2D에서 2D입니다.
그럼 요 세 번째 랩에서 한 건 요건 멀티뷰를 쓴 거 아니에요?
멀티뷰를 쓴 거가 아니라 그냥 거기 있는 데이터를 쓴 거예요.
거기 데이터 쓴 거라고요? 그럼 요거는 앞에 그거 한 거랑은 직접적인 관계는 없는 거예요?
거기를 통해서 그걸 통해서 레이블한 데이터를
레이블한 데이터를. 그러면 그건 완전 그라운드 트루스는 아니고 약간 일종의 약간 수도 레이블 비슷한 건가 보네요.
예, 근데 거의 그라운드 트루스에 가깝습니다.
예. 그러면은 이거를 트랜슬레이션을 그러니까 이게 뭐 약간 뭐 일종의 뭐 사이클 컨시스턴시 막 그런 걸 써가지고는 혹시 해보진 않았나요?
그게 이제 제가 사람들이 이런 챌린지를 통해서 해줬으면 좋겠는 부분.
알겠습니다. 고맙습니다.
저도 질문 하나 있는데요.
예.
그 아까 전에 KL 다이버전스 그 에피폴라 로스 펑션을 말씀하셨는데
예.
그 디스트리뷰션이 그러면 그 2D 그 이미지 전체에 대한 디스트리뷰션 간의 KL 다이버전스라고 이해하면 되나요?
예. 전체 모든 픽셀에 대한 KL 디버전스.
근데 그러면은 이게 그러니까 에피폴라 라인에 대한 디스트리뷰션이 나오고 그거랑 그 다음에 이제 그냥 다시 이미지에서부터 바로 찾은 디스트리뷰션 간의 KL 다이버전스라고 이해를 했는데 약간 서포트가 되게 막 달라질 수도 있지 않나요? 그래서
제가 그 부분을 좀 빨리 지나갔는데요. 예, 여기서 제가 여기서 트랜스포메이션 하는 걸 좀 많이 설명했는데 여기는 별로 안 했는데 간단하게 생각하시면은 여기 그 픽셀 프리딕션 한 거를 자기한테 프로젝션 시켰다고 생각하시면 됩니다. 이거는 다른 뷰에다 프로젝션 시키는데 이 트랜스포메이션 자체가 아이덴티티라고 생각해 보면은 자기 자신한테 에피폴라 라인을 썼다고 생각해 보면은 그게 여기 에피폴라 라인의 디스트리뷰션.
그래서 하여튼 서포트를 맞춰주고 거기서 디스트리뷰션을 거기서 KL 다이버전스 계산했다는 말씀입니다.
Yes, 예, 여기 이제 디스트리뷰션이 이제 이렇게
네.
에피폴 라인은 1D parameterization이거든요. 그냥 앵글로 representation인데 그래서 결국은 one dimensional 디스트리뷰션이 생기고 그거 두 개를 매칭시킵니다.
네. 그러고 여기 처음에 디스트리뷰션을 계산할 때는 뭐 약간 뭐 레이블을 가지고 조금 시작을 하고 이렇게 한다는 말씀이신가요?
예, so semi-supervised.
네, 알겠습니다.
질문 드려도 될까요?
예.
네, 안녕하세요. 저 문수목 교수님 연구실의 박정원이라고 합니다. 그래서
네.
재밌는 내용 잘 들었고 제가 약간 이 분야에 자주 잘 알지 못해서 나이브한 퀘스천일 수 있는데 제가 이해한 바로는 이제 그 라벨드 데이터를 이제 같은 시각에 이제 멀티뷰 카메라로 촬영한 다른 이제 사진 데이터로 그 라벨 데이터를 트랜스포해서 러닝에 필요한 그 라벨 데이터 숫자를 늘리는 방식으로 그 러닝을 잘 하도록 만드는 것 같은데 이때 이제 그 멀티뷰 카메라라는 게 결국에 그 하나의 상황을 여러 각도에서 찍은 사진이잖아요. 그래서 그렇게 이제 그럼 이제 그 라벨 데이터를 통해서 트랜스포 시켜서 이제 라벨 데이터 숫자를 늘려도 그 결국에 멀티뷰 카메라로 그러니까 찍은 상황 자체는 하나의 상황이니까 혹시 그런 부분에서 뭔가 제너럴라이제이션 성능이 좀 떨어지거나 그러니까 특정 상황에 있는 데이터만 이제 라벨링을 하는 거니까 혹시 그런 문제는 발생하지 않을까요?
예, 제가 그래서 처음에 얘기했던 데이터 어그멘테이션 그 부분이 지금 정확히 말씀하셨던 부분입니다. 레이블하고 그것들을 리컨스트럭션해서 다른 이미지에다 프로젝션 시켜서 그거를 데이터 어그멘테이션을 사용한 게 첫 번째 방법이었고요. 근데 이게 이런 방법들이 문제가 있는 게 그 프레임 자체도 우리가 레이블을 해야 되기 때문에 그 어노테이션의 개수가 되게 리미트돼 있을 수밖에 없어요. 그래서 여기서 지금 제가 보여드린 거는 레이블이 없어도 서로 인포메이션을 트랜스포메이션 할 수 있도록 한 게 지금 제가 보여드립니다. 그래서 말씀하신 대로 레이블 데이터에 대해서만 이제 트레이닝을 하면은 그 특정 상황, 특정 포즈에만 할 수 있는데 이제 이것들을 unlabeled 데이터에 대해서도 다 할 수 있으면은 그게 generalizable 되겠죠.
unlabeled 데이터에 대해서 이제 그 아까 말한 그 그 슬라이드에서 보여주신 프로젝션 같은 걸 이용을 해가지고 라벨링을 하는 걸로 제가 이해를 했는데 그거랑 약간 다른 건가요?
레이블링을 하는 게 아니라 그냥 서로 self consistency를 measure를 하는 거예요.
아, 네, 알겠습니다. 감사합니다.
뭐 간단한 거 하나만 또 물어볼게요. 이거
예.
카메라 이거 싱크로나이제이션 에러 같은 거는 거의 무시할 만한가요?
예, 이거는 나노세컨 레벨로 하드웨어 싱크로나이즈.
알겠습니다.
이거에 엄청나게 많은 돈과 에포트를 All right, so then let me just move on to the next topic. So I'm going to be quick. So far I've been talking about the relationship between data and the prediction. Due to the nature of the behavior data, so it's very challenging to obtain large annotated data for behaviors. So that's why I talk about the multi-view supervisions, or the way to use a multi-view geometry to transfer the visual information from one image to the other. And this allows learning the prediction model without labels in a self-supervised manner. However, this setting is still highly restricted because in many real-world scenarios, we don't have that multi-view camera systems. As the Professor Han already mentioned, yeah, I mean, we need to have this camera system, right? But there's not much system out there, right? So the question is, how do we formulate the self-supervision for the mobile cameras? Okay, can I use the video that I take from my cell phone camera? Can I use this for my training data? Okay. So the first idea is, of course, using a temporal consistency across time, right? So geometry and textures, what we observe must be consistent across time. So for instance, here I'm showing the video of unconstrained monocular camera taken by the cell phone cameras here. And we demonstrate to render the video that is almost comparable to the one that we produce from the multi-view camera systems. Okay, so on the right, this is the rendering result that we from this unconstrained monocular videos. So the one naive idea is just to transfer knowledge that we have learned from the lab and then to the testing environment in the wild. Okay, so that's like one naive idea. So we learn everything from the multi-camera systems and then transfer everything into my mobile camera. Okay? But it turns out that it doesn't really work well because the domain, there's a huge domain gap between the laboratory setups and the real world images. And you see that the tracking is highly unstable, and even the texture does not really match with the real image because the lighting is different between these two different setups. So instead, what we did is we come up with a self-supervised learning idea by enforcing some self-consistency. So consider this two images of same person, okay? One with open mouth and one with a closed mouth. although there are different expressions, because they are from the same person, it is expected that the skin texture should be consistent across time. And this is from the same video, so illumination is expected to be almost constant. Okay, so this is what I meant by the temporal consistency. Okay? Let's have a prediction. Prediction model. So here I have some prediction model that predict that can in the some canonical space, which is where we can factor out the geometry and expression. And note that the texture and the expression here is counted so that we can, so it has to be the consistent across the time. So by minimizing this texture, skin texture difference, we can enforce the temporal consistency while training a neural network. So this neural network is now defined by having this temporal consistency. And so this results in the high fidelity reconstruction of phase from the unconstrained monocular cameras. We can even render the multi-view phases from the using this self-supervision. Again, I can use my video from my cell phone camera to train my neural network, okay, by using this temporal consistency. So this is great, but the application is still limited because we need to have this training data from the multi-camera system. So this is very similar to the OpenMonkey Studio that I talked about. We use this multi-camera system to capture the monkey in the lab, but that is not really generalizable to the mobile cameras. Okay? So this means that every time we want to render person, we have to bring that person into the lab for this multi-view scan. So the question is, can we even relax the requirement of scanning the person from the multi-view camera systems? Okay. I argue that this is possible. Okay. For instance, here we explored some pose consistency by predicting the depths of human geometry from single view images. Here I'm showing the input image. This is the depth predictions, the surface normal prediction, and the mesh model reconstruction from these predictions. Okay. So, how it works? Okay. So consider this historic picture of Frida Kahlo. Okay. Now I'm going to train a neural network that can predict the 3D geometry of Frida Kahlo in the form of a depth. Okay. So I have a neural network that takes the input image and predict the output depth. And in fact, this is not even a new problem at all. I mean, the computer vision, the researchers have been training a neural network to predict the depth from the single view image for the autonomous driving or the indoor space navigation. Okay, so this is not a new problem. So that's what it is. So to train the neural network, of course, we need a lot of the data instance. It's a pair of image. So I need the image and the depth pair, so that we can teach neural network to perform this similar task. Okay? So then where do we get this data? Okay, for the this human cases. So one source of data can be the 3D scan human models. So there are CAD modeling company that scans a few hundreds of the humans using and such as Render Peoples or some other company that provided these 3D models for humans. Okay, so once we have this CAD model, we can render them to generate the image and the depth image together from the multi-viewpoints, and then we can use this synthetic data to train a neural network. So, so here's like one of result that I just use a neural network to predict the depths, and here's a depth prediction surface normal, and this is a reconstructed mesh out of this. It captures some geometry. I see the face, I can recognize a hand, but the fidelity is pretty low. Okay? The face is heavily blurred and the wrinkle is overturned. The main source of the error comes from the limited amount of training data that is not generalizable to the training data, the testing data. So let me quantify the size of the training. So I'm showing the number of data instances for the data set used to predict the depths of indoor and outdoor scenes. For instance, ScanNet data. Okay? ScanNet data set that is made of the millions of image samples in indoor space that include the furniture, objects, and flora, and so on. Okay? And you see that the order of the data size is few million scale. Okay? What about human data set? Here are the few data set that used in the literature. Okay? It is way smaller than the scene data set and few thousand scales instances. And the size of data is at least an order of magnitude smaller than the scan data, the scene data, which makes it very difficult to generalize to the new person. Okay? Further, our appearance is way more complex. It is a factor of clothing, apparel, styles, pose, and illuminations. And there are so many factors that participate in contributing to generate a different appearance. Therefore, the building a generalized model that spans all possible visual appearance with a 3D scan model is practically infeasible. So we need better data resources that can express such a diversity. So we address this challenge by using a video data in social media. TikTok, a mobile application, include extremely large diverse data. Okay? There's a huge community of users who voluntarily upload the short dance videos ranging from 15 to 30 seconds. And due to the voluntary nature, there exists a sheer amount of the visual data readily applicable for training a neuron. However, the neuron, using this social media data is not as simple as I thought. The secret behind the training a neural network is the requirement of the ground truth data. Okay? I need to have image and a corresponding 3D ground truth. But there's no such data for the social media data. I mean, I don't have the depth data that can teach my neural network. So what should I do? Our idea is to use the post self-supervision, enforcing the self-consistency within the video based on the underlying geometric relationship across the frames. So consider this two image, okay, so with a different pose, okay, the same person, and this two image shows a different pose of the person, therefore the different 3D geometry. However, since this is from the same person, the same video, okay, the 3D shape of this person must be similar up to some rigid transformation. What do I mean by that is that let's say I have a neural network that predicts the depths of this person. Okay? And there exists a corresponding body part. So this lower arm is correspond to another lower arm in the other image, okay? Which indicates that in 3D world, the depth image can be transformed to the other image using this correspondence. So for instance, we can think of the depth as a 3D object. So this depth can be think of this as 3D objects that undergo some rigid transformation and rotation and translation to form a target 3D geometry. This means that even though I don't have a ground truth 3D geometry, I can still enforce a self-consistency between two images, resulting in self-supervision. Okay? I can still expose my neural network to this social media data, okay, without 3D ground truth. So here's we apply the geometric transformation. So using this transformation to transfer the information in one image to the other image. By minimizing difference between these two images, we can actually enforce a self-consistency. Okay? So here's some of the qualitative results that we have: input image and depth and surface normal, and this mesh model we reconstructed for this teenagers and TikTok data. And here's another example. A teenager playing and dancing, playing the TikTok dancing. And by the way, this paper got the best paper honorable mention award for this CPPR. Right, so we can reconstruct a grayscale image of the Frida Kahlo that captured drapey shoulder dress. And also we can even see the Mona Lisa painting in 3D space. And this is my favorite example where we can reconstruct this is statue image where we can reconstruct the underlying facial geometry over this veil. So in sum, I presented my research focusing on the behavior image that models the geometry of human and animals. And the key challenge lies in the difficulty of obtaining a label data. And I've shown a few examples of self-supervision that use a multi-view, pose, and temporal consistency. So before I conclude, I would like to acknowledge my team where nothing is possible without their tremendous effort. And thank you for listening.
네. 발표 감사드립니다. 혹시 질문 있으신가요? 아까 전에 전반부에 관한 질문들이 좀 있었고
저기 그 컨시스턴시를 찾을 때 그 비디오 간의 컨시스턴시는 그러면 옵티컬 플로우에 그냥 의존해서 찾는 건가요?
옵티컬 플로우를 이용할 수도 있고요. 저희가 지금 여기서 사용한 거는 그 포즈 코레스폰던스라고 해서 댄스 포즈 같은 경우 그 바디 간의 그 파트 간의 그 댄스 코레스폰던스를 찾아줍니다. 그래서 그런 코레스폰던스를 이용했습니다.
네, 그러면 그럼 이해됐고, 그리고 하나 좀 의문인 게 있는데 이렇게 윙클이 있는 클로즈 같은 경우에는 컨시스턴시를 찾는 게 오히려 도움이 안 될 수도 있는 거 아닌가 싶어서 피더리티랑 정확도랑 좀 다르지 않나 싶어서.
다시 말씀해 주시겠어요?
예를 들어서 비디오에서 이제 컨시스턴시를 찾는데 이제 클로즈 같은 부분에 대해서는 윙클이 계속 바뀌게 되는 거잖아요, 프레임마다. 그런 경우에 대해서는 오히려 이런 컨시스턴시를 주는 게 도움이 안 될 수도 있는 거 아닌가 싶어서 질문 드려요.
네, 좋은 질문입니다. 네, 맞습니다. 그거는 저희 이 아이디어의 리미테이션인데요. 그래서 저희가 지금 저널 버전으로 하는 것들은 이것들을 리지드 트랜스포메이션이 아닌 뭔가 좀 더 플렉서블한 트랜스포메이션, 뭐 어파인이나 뭐 퍼스펙티브나 뭔가 좀 non-linear 트랜스포메이션으로 할 수 있는 방법을 지금 생각하고 있습니다.
네, 알겠습니다. 그러면 결국 댄스 포즈에 대해서 하는 거니까 좀 피더리티 같은 예를 들면 뭐 스커트, 치마 같은 거 입은 사람이나 그런 거에 대해서는 적용이 안 되고 있는 건 맞는 거죠?
예, 그런 부분은 아무래도 리미테이션이 있습니다.
네, 감사합니다.
네, 혹시 또 질문 있으신가요? 네, 없으시면은 이제 시간이 된 것 같아서 그러면은 이번 세 번째 발표를 여기서 마치도록 하겠습니다. 다시 한번 좋은 발표해 주신 박현수 교수님께 감사드립니다.
감사합니다.
네, 감사합니다.